making dinner. I almost.
Okay, so quick review. If you were gonna draw the Bohr model of the atom, what would you draw?
Oh. Which one was that one?
If you were to draw the model of the atom, what would you draw?
Like circles in the middle.
Circles in the middle. What are those circles represent?
Nucleus.
Nucleus.
And then like the electron complex, so maybe like a circle with some like dots on it.
Okay.
Yeah.
And those are the
Electrons.
okay electrons. Okay. Anything special about the nucleus?
It has protons and neutrons.
There's protons and neutrons. Okay. If this were a hydrogen atom, how many protons would it have?
At this point, I think you just need the markers.
Well, that's what I just said.
One.
Very good. One. Okay, so this is hydrogen and that's one. Man, this one's even really bad. Okay, good. How many electrons would it have?
Here. Try this one.
I don't know. I'll just keep going.
You're gonna run out of markers. What were you asking? What?
How many electrons?
I think one.
One, yeah.
Okay, I was like.
Okay, so electrons one. Oh, see, there it is. Alright. So yeah, if this were hydrogen, it would have one proton, one electron. What about neutrons? Do you remember what neutrons do?
They like equal it out.
They do help that. There was an I word.
Isotope?
Yep, isotope. So if we have different numbers of neutrons, so neutrons is not set. It's like, well, how many neutrons? Well, it depends on which isotope we're talking about. Alright. Alright, so we're not going to worry so much about neutrons, because they don't always have to be a set number. Okay. How would helium be different?
It would have two.
It would have two protons,
Would it also have two electrons?
two electrons. Yeah, okay, good. Alright, so if we've got the electron there, there's the electron there. So this is hydrogen, there's its electron. Okay. It has one electron. For helium, it has two. Where is that other electron going to be?
In the cloud.
Someone volunteer. Put a dot where you think that electron's going to be.
Are we just guessing?
You were just guessing. 'Cause
I'll make a dumb guess, but I'll guess.
and then, but then think about it. So if you put it there, like, why would you put it there?
I don't know. Because you said to guess. Would it go on the answer?
Put a dot. We'll talk about it.
Right here. I don't think that's right at all.
Okay, good. Okay. Fine.
Here you go.
Because if we're going to talk about lithium, now how's lithium different?
Lithium has
Three protons
and electrons.
and electrons. Okay, Noah.
Your turn.
Where's that third electron going to go?
I don't feel confident in my answer anymore.
Okay, good. Beryllium.
Four.
Where's the fourth electron going to go?
Add his turn. Oh. I guess. It's okay, that's what all of us did.
How come you didn't put yours like on the little dotted line?
I was guessing.
Okay. you know, when we look at a picture and we see, oh, the electron is there in the cloud, whatever we want to call it, the orbit of the cloud. What is the electron doing? Is it just like stationary right there? So that when we, because I think we understand when we go up the periodic table and as we add electrons, those electrons have got to go somewhere. And so are they just stationary in those spots? So then, just guess. How many electrons can we fit around there? If we're gonna put them all around that ring, because when we get up to iron, how many are we gonna need?
A lot.
Look at your periodic table. 26. We're gonna need 26.
See that?
Okay. When we get up to lead, how many are we gonna need? 82. So are we gonna be able to fit 82? Okay, and I'm gonna agree, but we need to think about why we cannot fit 82. We can't pack 82 around it like that.
Wouldn't they like bump into each other?
Okay, go with that. Can they even bump into each other? Why not?
Well, is it like magnets where if you have two of the same
It's
it
all negative.
like bounce off?
So we know something about electrons, right? Electrons are negatively charged, protons are positively charged. So as we start to fill them in here, right, 4 is fine, like if they just stay equally apart, then they all equally repel each other. Okay? But at some point, when we get 82, or what about uranium? 92. There's 10 more. What's going to be the problem?
They'll like start bouncing off each
They're
other.
gonna be
repel
practically
each other.
touching.
Yeah, they're going to be practically touching,
They don't do that.
and so then what are they going to, what's going to be the result? What are they going to want to do?
Like
Well,
expand.
Bounce off
Yeah.
each other.
Yeah, expand, right? Is we can't fit them all in there together. Okay. Well, this is a good idea, right? And it leads to why people were thinking about how the electrons are arranged and like, okay, what are some of the characteristics of the model, right? Can we look at it like this? Because as we get bigger and bigger elements, like this is not going to work. It works for hydrogen. Why?
Because it's just one.
Yeah, it works perfect. But as we get elements bigger and bigger, that model doesn't work. So then we need a new model, right? We need a new model that will work for all the elements, not just one. Okay, and that's a big idea, right? We need a model that will represent all the elements, not just one. Okay. But we're going to look at hydrogen because Bohr's model, when Bohr put his model together, it worked well for hydrogen. And the reason it did is because it only had one electron. And so he could describe all the things about it, and it worked great. But when we applied that to other elements, it didn't work so well. For the very reason electrons want to repel each other. And so it doesn't work. Okay?
So they are like a magnet.
You can think of it that way. Think magnetism, because we're going to talk about that today. That's not going to be the first time we talk about it.
It just makes sense in my mind.
Right, yeah, because they have charges, right? Like a magnet, kind of. And so that's going to be an important part. Why does the electron stay connected to the nucleus?
Because it's like with the neutron they're connected. Positive.
What's-
It like repels from the negative?
No. What do opposite things do?
They like connect, like stick together.
They attract.
Yes.
Opposites
Thank you.
attract. Like things repel.
Yes.
Right? So the electron stays with the nucleus because the nucleus is a positive charge with all the protons. So that's what it's saying. Okay. But once we start putting a lot of electrons around there, they're going to repel each other. You know, as we think about this more and more and more, is the electron like Earth orbiting the sun in this path? Or is it something else? We'll find out. Okay. So, to fully understand all of this, to fully understand how this model is going to work and what Bohr was thinking and then how other people proposed other ideas, we need to understand what light is and why light works. Because where light comes from and electrons are very closely tied together. Okay? And so, Layla, do you want to start on the top of 91? Start talking a little bit about light.
So like that very top area.
Yep, the Rutherford model.
How do you say that?
The Rutherford model?
Okay. The Rutherford model of the atom was an improvement of the previous models, but it was incomplete. It did not explain where the atom's negatively charged electrons are located in the space surrounding its positively charged nucleus. And after all, it was well known that oppositely charged particles attract to each other. So what prevented the negative electrons from being drawn into the positive nucleus?
I know you want to go next one.
In the early 20th century, you are talking about evolved as a result of investigations into the absorption and emission of light from matter. It started to reveal an intimate relationship between light and atoms of electrons. This new understanding led directly to revolutionary view of the nature of energy, matter, and atomic structure.
Okay, so a couple significant things. One, if this is positive and this is negative, why doesn't the electron fall into the nucleus? Why doesn't the Earth fall into the sun?
Because the magnetic field or something. I don't remember what it's called.
As the Earth, what are we doing?
Spinning.
We are spinning. Yep. And what else?
Orbiting?
Orbiting. Which means what?
Like going around the sun.
Going around, because it's winter now,
Yes.
and later,
It'll be summer.
because
The sun.
we're not in the same spot.
Yeah.
So the Earth doesn't fall to the sun because we are moving that way.
Yes.
And so we're always
Moving.
moving. Okay. Alright, so why doesn't the electron fall into the nucleus?
Because
The electron must be
rotating with it.
orbiting.
Yes. That word.
Orbiting. Okay, important vocabulary, orbiting. Okay, so the electron, if we're trying to reason why, because they said, in here it's like, so what prevented the negative electrons from being drawn into the positive nucleus? Well, why not? Because in Rutherford's model, what was it the characteristic of the nucleus? Positive. If electrons and protons were mixed together, would the nucleus have a positive charge? Or would it be neutral? Well, if you have a positive and a negative,
It's supposed to be neutral.
it'd be neutral. Okay. And that's not what Rutherford found. Rutherford found nucleus is positive. So the electrons are not there. Okay, so, but what prevents them from falling? Well, they must be orbiting.
Yeah.
Okay, so they must be moving. All right. Oh. Hey, so if we're on this like whole planet thing, if here's the Earth, what's out here? What's the next one out? This is Earth. This one is.
What's the one closest to Earth? Is it?
Or what's the one in here? Venus. I'll give you this one. This one's Venus. This one is
Oh yeah, Mars?
Mars.
Yeah.
Oh, okay. So maybe so as we put this whole model together, if we're thinking about it's like planets, then there isn't just one orbit.
No.
We can have closer orbits and farther away orbits. Does that seem reasonable?
Yes.
If we're going to think about it like the solar system.
That makes sense.
That makes sense. Okay. And then like Layla says, not only are we orbiting, but we are also what? Spinning. Okay. Go with this whole solar system. All right. So, this is an interesting idea. Light's an interesting idea. Maybe they are related to each other. So, Abby, you want to read the problems of
Yes.
that?
Before 1900, scientists thought light behaved solely as a wave. This belief changed when it was later discovered that light also had particles like characteristics. Still, many of light properties can be described in terms of waves. A quick review of these wave-like properties will help you understand the basic theory of light as it existed at the beginning of the 20th century.
Okay. So, waves. What do we know about waves? Okay, so we're going to think about water. Okay, so you have a surface of water. Okay, it's your bathtub and you filter your sink up. Okay. In order to get a wave, in order to disturb the surface of the water to make a wave, what do we have to do? Look at it really hard. Talk to it. Make a wave. What do you gotta do?
Is it like motion?
Yeah, what do we need to physically do to this water to make a wave?
Like
Disturb it.
Yes, okay, good. We have to disturb it, we have to touch it. Okay? So we're gonna touch it. In physics terms, then, like, what are we doing to the water? Like, when we touch it, what are we doing to it?
Disturb it.
Yeah, I know, but I want you to use some like technical terms. I mean, we're gonna. This is
So
gonna be
what's
like.
the technical term?
This is gonna be like really basic. We just want to then use the words, the right words, because those will come into play. Those will be very important.
And I don't know
So
what the right word
if
is.
we
What's the right
touch something to make it move, what do we do? Apply a force.
word? Good job, Noah.
Okay? Right, we touch it. Right? So we apply a force to the surface of the water. Okay? And let's just say we're gonna touch it, or we're gonna drop something into it. So the direction of the force is down. Okay? When we do that, now what is for just that instant, what does the surface of that water look like when we push down on it?
Ripples. You know?
But just in an instant, just in that one instant, when we push down, right? Does the surface of the water stay level?
No.
No, the surface of the water,
What?
like where we push it down,
Yes.
right? Boom. Okay, but now we know, we know what happens,
Yes.
okay, it ripples. Okay, so we touch it, we apply a force, it pushes down, and then it ripples. So then, a moment later, does it look like this? No, what happens to this area here?
Moves down.
It moves,
Mhm.
okay? Now, if we touched it in the middle of the water, what would that look like versus if we just touched it on the edge of the sink? I mean, we'd recognize that's gonna look a little different, right? Okay. But we're just looking at it from the side. So, a moment later, right, we know that it's gonna move
Yes.
away from where we touched it.
Yeah.
Okay, so we apply a force that causes movement. How do these two directions compare to each other?
Well, they're both moving out.
Well, how does the force arrow compare to the movement arrow? Think geometry. What is that relationship?
They meet.
It's a P word.
Oh,
Parallel? No.
no.
Well, this is parallel.
I know.
Perpendicular.
Thank you.
Perpendicular. Alright, so good. These are perpendicular to each other.
I haven't taken geometry in a while. Okay.
Right?
It's
We
been like
push
2 years.
down, the wave moves
That way.
perpendicular.
Yes.
That's another good word. Perpendicular. Okay, so let's think about some things. What if I wanted the water to go down farther? What would I have to do?
Press harder.
I'd press harder.
Add more force.
Force.
Good, yes, okay. Would that change anything about how the movement?
It'll move faster.
Will it move faster?
Yes. I mean, if you add more force, it like pushes away.
Okay.
Quicker.
Okay, this is,
I.
well, think about it.
Am I wrong?
Alright, so,
It'll be bigger.
this one's gonna move away, it will be bigger, it will be bigger. So if we added more force, then it would look like that, then like that. But that's a good question, like, but will it move away faster or slower or the same speed?
I mean, when you like throw a bigger rock into the water, it like pushes away bigger waves
Mm-hmm.
and like faster than if you throw a small rock.
Okay, that's a good idea, and I'm not gonna say one way or the other. Because that's not really hugely important right now. This is the other thing that's more important, okay?
Okay.
What happens if I press and then press again?
We take multiple waves.
Makes multiple waves, so let's do that. Okay, so now we have 2 waves, okay. So now let's think about some things. Okay? What if I wanted these 2 waves closer to each other?
Then you gotta like faster.
I got a fast time, so time.
Mhm.
Right? So time is an important thing. So I could measure the time between these two, right? And so I could say, well, if I did this one in 1 second, you know, at time 0, and this is at time 1 second, so 0 seconds and 1 second, then those waves are 1 second apart. And if I wanted them to be closer together, I would have to force it faster, like I'd have to do it faster. If I wanted them farther apart, I could do it 0 seconds and at 2 seconds, and the waves would be farther apart. Like, do you agree with that? Like, that seems okay? Okay. But, so not only are these a time apart, but I could actually, if I could stop it, I could actually measure this to see exactly what the distance is, right? So not only are they a time apart, but they are a distance apart, so I could measure in meters or something, or centimeters, something like that, and I could get a distance apart, okay? So then are time and distance dependent on each other?
Yes.
Or are they related to each other? Yes, time and distance are related to each other because the faster I would press, the shorter the distance. Does that make sense? And the less, I'm going to use the word frequent I press, the larger the distance. Okay. What else do we need to think about here? Alright, so I apply for it, we agree, and so now this is where we're having this question with Layla. Does time or distance depend on the force if we just push it harder? So that question's still up. So I'll let you think about it. Okay.
Well, in my mind, it makes sense.
I totally understand. Okay. Oh. If we have time and distance, like when we press, how fast is this one moving away? Whatever, right? Because I want to think about, like, how could I change the distance between these two waves? Like, because if this one was moving away faster,
Well, it might appear faster because it's bigger. Like,
I agree.
with more force, it looks bigger, so it might look faster than if you use something small.
I agree. So maybe just looks like it. Or
Maybe. I mean,
But do we see that, like, when I press the first wave, if that one moves away really quickly, then what is my distance going to be between waves? Like if I press it 0 seconds and I press it 1 second, if that wave
1
moves away
second.
really quickly, it's the same time. What happens to my distance? Longer, because that wave moved really fast away. Okay, so it's further away. Because we're talking about water, but what if I'm in like ketchup? Or something. So I plop it into ketchup, and that wave just barely moves. So what happens to my distance? Shorter, right? So speed is another thing here. Like how fast is that wave moving? And that is, I mean, time, distance, and speed, those are all going to be related to each other, which is an important idea. In water, how fast will a wave move in water? Visualize a surfer paddling.
depends on the current.
Yeah, it depends. But can you see like a person on a surfboard kind of keeping up with the wave? Like, because they're on the wave, they're trying to be on the wave, and so they're paddling.
I mean, it really depends on how if the wave is moving.
But is a wave moving so fast that a surfer couldn't keep up with it?
No.
No.
Unless they're really slow.
Unless they're really slow. But you know, when I've seen surfers, or I watch videos of surfing, or I watch Surf's Up with the penguin guy, like they can keep up with the wave until they get on the wave, and then they're on the wave.
Yeah, in California, we got to watch the the championships from there was people from Peru and everything. 'Cause
Oh,
we
yeah?
went to the beach for FBLA,
Oh, cool.
and they were having a competition on one side of the beach, so you could go up on the, I I don't know those things. Those like deck things, yeah. There was people from all over and you could like watch them. It was really cool.
Uh-huh. Cool.
Yeah.
So a water wave isn't hugely fast. Because I want to compare that with a sound wave.
Okay.
Okay. How fast is a sound wave moving? How fast is that?
Really fast.
Really, I mean, when we think about an airplane breaking the sound barrier, how fast is that plane moving?
Pretty fast.
Crazy fast.
Faster than I can swim to keep up with it?
Oh yeah.
Oh yeah, so we recognize that not all waves are gonna move at the same speed. So that's where the ketchup and that or syrup. So we're talking about water. Sound out here, what's the sound moving through? There, sound's moving through there.
Yeah.
Okay. And so that wave is gonna move at a different speed. Okay? All right. Do we feel comfortable about waves?
Yes.
We know some stuff. There's some words.
We learned some new words.
Some words. Okay, so boom, the wave description of light, Layla. Read that first paragraph.
Visible light is a kind of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. Other kinds of electromagnetic radiation includes X-rays, ultraviolet and infrared light, microwaves, and radio waves. Together, all the forms of electromagnetic radiation form the electromagnetic spectrum. The electromagnetic spectrum is represented in figure 4 and through 1. On page 92, all forms of electromagnetic radiation move at a constant speed of about 3.0 times 10 meter per second through a vacuum and a slightly slower speed through matter. Because air is mostly space, the value of 3.0 x 10⁸ meters per second is also light's approximate speed through air.
Okay, no.
The significant feature of wave motion is its repetitive nature, which can be characterized by the visual properties of wavelength and frequency. Wavelength is the distance between corresponding points on adjacent waves. Depending on the particular form of electromagnetic radiation, the unit for wavelength is a meter, centimeter, or nanometer, as shown in figure 4. Frequency is defined as the number of waves that pass a given point in a specific time, usually 1 second. Frequency is expressed in waves per second. 1 wave per second is called a hertz, named for Heinrich Hertz, who was a pioneer in the study of electromagnetic radiation. Figure 4.2 illustrates the properties of wavelength and frequency for a familiar kind of wave, a wave on the surface of light. The wavelength in figure 4.2a is a long wavelength and a lower frequency than the wave in figure 4.2b.
Okay, so some good stuff. First, when we talk about light, it is electromagnetic radiation and it is energy. If we remember our definition for energy, right, force is applying. Force is an acceleration over a distance, right? Okay. But what's energy? Ability to do work. Can a water wave do work? I mean, kind of, right? I mean, so if this wave crashes onto the shore, does the shore stay untouched?
No.
No, what happens to the beach?
It has waves. Or like,
What happens to the sand?
yeah.
The sand moves. Okay, so this wave, even if it's the water wave has the ability to do work. Because if it crashes on a beach, and washes up the sand, and it moves the sand, that's work. Okay. Light is no different. So light, being this wave, has the ability to do work. You can kind of see this when you sunbathe. Is the temperature of your skin unchanged when you sunbathe?
It,
Or yes,
warmer.
Okay.
It warms up,
Yeah,
so it changes it. So
warmer.
that's work, right? So the sun, the light from the sun is
And if you
working
get
on your
sunburn,
skin.
your skin is like hot.
Alright, so it can do work. Alright, that's a good idea. Light has a speed. How fast does light move? 3 times 10 to the 8 meters per second.
Yes.
A lot faster than I can paddle
Yes.
to keep up with it, right? We looked up sound, because a plane can fly as fast as sound, right? So we looked at it was like 710 miles per hour, which works out to about like 430 meters per second, if I remember right. So sound moves at 430 meters per second through air. That's pretty slow compared to 300 million meters per second for light. Okay, so light has a speed, but we can see why, right? Because light has these waves, and they are traveling. There's so much time between waves, and there's so much distance between each wave, and so we know speed is distance divided by time. So makes sense. Oh, and then wavelength. So then, what do we call the distance between waves? Wavelength. Okay, so that's a real thing. We can talk about that. And then, we already said this, right? How frequently are we doing this? So frequency we'll call it, is how many waves pass a point at a given time. So you're standing here, and we're counting how many waves go by. 1, 2, 3, 4, 5. And so we count up how many waves, and that's the frequency. Okay. Frequency is given in waves per second. Okay. And then what's the special unit? There's a guide. Hertz. And so Hz is the unit that we use for frequency. Waves per second. Okay. Let's come back to this because we didn't really define this. This is the only thing we did define. If we press this hard versus this hard, we see that the surface is pressed down so much. It's displaced so much. Do you know what that is? Like if we change how far we displace it, do you know what that is? That's okay. Amplitude. So when we press harder, when we apply more force, that changes the amplitude of the wave. When you hear amp, what do you think?
Something with a guitar.
Something with a guitar.
Isn't that what the, like, what is it?
Yeah, amp. What does an amp do for a guitar?
So it changes how like deep, like it doesn't change how like deep or like high the song is or something, like, you know,
Is it?
something like, yeah. Or does it like move the strings?
No,
No, I strum on it.
yeah. Isn't the amp the thing that's connected to it? Like the,
Uh-huh.
yeah, like this little
Uh-huh.
speaker thing.
The speaker.
Thank you.
The speaker. which does what to the guitar sound? If I'm not,
It makes it louder.
it makes it louder.
Yeah.
Alright, so this is
Thanks, Noah.
this is an important thing for sound. We can talk about it for live, but for sound, when you change the amplitude of sound, you make it louder. That's how we hear it. Okay? Because what is the amp doing? What is the amplifier doing?
It's making it
Oh, adding
bigger,
force.
the wave's bigger.
Right, it's adding
Force.
energy, it's adding force
Yes.
to
Make it louder.
make it louder, and then it plays it through the speaker so we can hear it.
Yay.
So that's what we do.
See, the only reason I know that is because Nick has a guitar. He doesn't play it, but he has one.
Okay. All right. I bet we can answer your question now. So
What
now that we know that making it deep, adding more force makes it louder.
Yes.
When I'm low versus when I'm high. Now what am I changing? Because I'm not changing the loudness. I'm changing what?
The
Pitch.
tone?
I'm changing the pitch.
Good job, Noah.
Right, so if I'm low, that's a certain pitch, or if I'm a bass.
Yeah.
And then if I'm a tenor, and then if I'm a soprano. Right?
Yeah.
It's not really louder.
No.
I mean, I
it's
could
just,
try to make it all the same loudness, but change the pitch.
sometimes
So I
the
didn't
pitch
change.
sounds louder, but
I didn't change loudness. What did I change?
the
The frequency.
I changed the frequency. Right? So a low voice, bass has a low frequency. So low frequency means how many waves do I have per second?
You have less waves per second.
Let's say 10. So my frequency is 10 hertz.
yes.
10 hertz. Okay, but then when I got higher,
Two? Could you look up?
I have 2 would be lower,
Yeah.
Oh,
so
yeah,
it would
yeah,
be
But-
15.
like 15.
Yes. This is
Ah.
what is highest.
Ah.
You let me sit there and struggle trying to figure out the words for the speaker. Stop judging my
Wednesday, donut.
Because
Got it. Okay.
if you ever look at a butterfly, its body is really long, but its wings are a lot bigger.
7.
Okay, but have you ever actually
Okay.
looked at like
Sweet. All right.
the? Okay.
Okay. Did I change how fast the wave was moving?
No.
The air still, the wave's still moving through air. I just change how often I do it. So this is an important concept. I'll give you another vocab word. Okay? Because repetitive. How do I get more waves?
When you're like,
Faster.
Repetitive.
Yeah.
Repetitive. What do we call this? Like a back and forth, or an up and down, or a forward backward oscillation.
Yay.
Okay, so I have an oscillation, and so, all right, this repetitive. And this is an important idea, right? Back and forth, like forward and backward through the same thing. So, an oscillation, I go forward and I go backward through the same path. Okay, like a pendulum.
Yes.
I swing. I'm swinging on a swing. I swing forward. I swing backwards through the same path.
Yes.
Okay, I'm oscillating.
Cool.
Oscillate. Cool. Okay. All right. So we know all this about waves.
Yes.
Okay. Push down, changes the amplitude, more waves, less waves, time, wavelength. They move the speed. Oh, so these are related to each other, right? Oh, let's read that. So who's up next?
me, I think.
Addie, just that first little thing right on the top of 93.
Of what?
93.
93? The frequency?
But it's going to tell us how to relate it.
Frequency and wavelength are mathematically related to each other for electromagnetic radiation. This relationship is written as follows. C equals, what is that?
Lambda.
Lambda V.
Yeah, so it says in the equation, c is the speed of light. Okay, so speed of light, c. C is the speed of light. That symbol is lambda, is the wavelength. Wavelength. Backwards, upside down y. Wavelength. Okay? And v is frequency. Now, some textbooks are going to use V for frequency, some textbooks might use this little funky F. I'm going to use the funky F because I like it. It's like, oh, how do I remember what frequency is? F. That makes it easy. So C, the speed of light, is the wavelength times the frequency. Distance divided by time. Speed. And I think we kind of understood that if we increased the time, what happened to the wavelength? Decreased. So if we increase one, we decrease the other. If we decrease the time, then they get shorter. So, increase the time, increase. Did I say that right? I think I confused myself. Increase time, take it shorter. That's right. Okay. Thoughts, questions? Okay, we're almost to here. We're almost back here. We're getting close. So, for a long time, this is how we understood light. Okay? And so studying light, all this stuff applied to light. The other thing that we haven't talked about, which is another thing we do. Can sound be reflected, or can waterways be reflected? Like they come one way and then they go back the other way, they're reflected? Can light be reflected off of the surface? Yeah. All right. So when we do all that stuff, right, light behaves just like a wave. Right? It can be reflected, deflected, refracted, right? All the fancy light stuff. If you do like convex and concave lenses and prisms and those kinds of things, like light does all this stuff. Okay? But then somebody throws a wrench in it and it's like, ugh. Well, maybe it's not just the wave. Maybe it's like a particle. And so that's where we get this next idea. So Layla, that first paragraph on the photoelectric effect.
In the photoelectric effect?
Mm-hmm.
Okay. In the early 1900s, scientists conducted 2 experiments involving interactions of light and matter that could not be explained by the wave theory of light. The experiment involved a phenomenon known as the photoelectric effect. The photoelectric effect refers to the emission of electrons from a metal when light shines on the metal, as illustrated in figure 4.3.
Okay. So this is where we're going to get these two ideas together. And why is it electromagnetic? Okay. So this is a little photo tube. And you can kind of see how it's set up in the diagram there. There's a metal plate, a curved metal plate, and then there's a metal pole. Okay, and so in this photoelectric effect, so this is in the early 1900s. When light, if we shine light onto that metal plate, it generates an electric current in that metal pole. So they're like, okay, well, what must be happening? Well, they are like, well, you've got this metal plate. When light hits it, it must be shooting off electrons. So these electrons shoot off of the metal plate and get, since it's curved, they get directed at that metal hole, and voila, it's almost like a battery or like a solar panel, and it generates an electric current. Why? Well, that's a good question. And we've seen fancy glass tubes with stuff in them before, right? When I showed you the cathode ray tube, right? If we go backwards, like if we put current into it, then the electrons are emitted and it caused that green light. Okay, well, we're just going to go backwards. We're going to try to do it backwards. Well, it works backwards. Okay. Okay. So then we got to think about this. Okay, so when we shine light on it, and we have to think about we have to broaden our definition of what light is. So if you look at that chart on the top of 92, like what is light? Okay. Now you see the color spectrum. Okay, that we know that's light. That's light we can see. But then what's just to the left of the visible light? Ultraviolet. What's just to the right? Infrared. Also light. Also electromagnetic radiation. But can we see it? No, we can't see it. But it's still light. Okay? If we go all the way to the left, that's gamma rays. So gamma radiation. Okay? If we go all the way over here, radio waves, short wave, and long waves. Okay? All light. If you look at the scale, let's pick radio waves. Radio waves are about how long? 10 to the 1 meter, so 10 meters. Okay? So 10 of these, about the length of the room. Right? So from wave to wave, it's 10 meters. Okay? Visible light is about what?
What,
10 to the third nanometers. Well, on our scale, where's nano? Really short. 10 to the 8 nano. Okay. So we have waves that from wave to wave is like 10 meters, or wave to wave is you can't even see. Right? I can't even use this to measure it because they're so close together. Okay? So when we shine light on this, we don't necessarily have to shine visible light on it. We can shine lots of different kinds of light on it and get a different effect. Okay? And so what kind of an effect did they see? No. Right? Are you on that? Okay. The mystery.
the photoelectric effect is on the frequency of the light striking the metal. For a given metal, no electrons are emitted if the light's frequency is below a certain minimum, regardless of how long the light is shown. Light is known to be a form of energy capable of knocking loose an electron from the metal. Like the wave theory of light believes that light at any frequency gets high enough energy to eject an electron. Scientists can explain why the light had to be of a minimum frequency in order for the photoelectric effect to occur.
Okay, so I've got light with a particular frequency and I've got light with other frequency, and for a given metal, no electrons were emitted if the light's frequency was below a certain minimum. Alright, so let's have some frequency. We have a frequency of like 1, 2, 3, 4, 5, 6, 7, right? There's our frequencies. Okay. And below a certain minimum, let's pick 4. Right? there wasn't an effect. After that, there was an effect. So how do we describe this? Or what's the explanation? Okay, Addie,
Okay.
the particle description of light.
The explanation of the photoelectric effect dates back to 1900s, when German physicist Max
Planck, yeah.
was studying the emission of light by hot objects. He proposed that a hot object does not emit electromagnetic energy continuously, as would be expected if the energy emitted were in the forms of waves. Instead, how do you say?
Planck.
It suggested that the object emits energy in small specific amounts called quanta.
Quanta.
A quanta is a minimum quality of energy that can be lost or gained by an atom. Planck proposed the following relationship between a quantum of energy and the frequency of radiation. E equals hv.
E equals hv. Okay, so we got this photoelectric effect idea. We got Planck doing some work. Here's what he proposes. Okay, he proposes that light is a particle. Okay, and it's got so much energy. Okay, and I'm gonna go over here. I think maybe. Let's see. Oh, that worked. Perfect. Okay. All right. So there's the metal plate in the phototube, and I shoot light at it, and it has a frequency. All right. Okay. What can I change about my light? I can change the speed, or I can throw it faster, but can light change speed? No, light can't change speed. So the speed that I throw it can't change. Okay, what else can I change?
Like the time you throw it, like if you throw
How
it
quickly you throw it?
faster.
How quickly I throw it. Okay, so if I throw it more quickly, what am I changing? I am changing the wavelength. The wavelength gets
Frequency.
shorter, and the frequency gets
Higher.
higher. Okay, good. All right. So at a particular frequency, nothing would happen, right? At a low frequency, nothing would happen. But then at a particular frequency, right? A little bit. Right? At a particular frequency, all of a sudden something happened.
Why? I see that. But why?
All right, something would happen. But what if I did faster?
Higher?
Would anything else happen? No, right? I just had to reach the minimum,
Yes.
and something would happen.
Okay.
All right. So at a low frequency, nothing. But then as I increase the frequency, all of a sudden something happened. But at a higher frequency, nothing else happens because it already happened. So the light had to have a particular set frequency where the thing would actually happen. He's like, oh, we'll call that quanta. It had to have a particular quantity in order for something to happen. Okay? So he does a little work and he's like, okay, the energy, the quantum of energy, so the amount of energy needed is related to the frequency, right? Think about the frequency. And a number that I had to invent. So we call it Planck's constant. And so energy equals frequency times Planck's constant, which is a number that he came up with to kind of help relate these two things together. So, putting all this together, now they could explain why some metal would not emit electrons. And so there we are. We have our model of the atom with the electron. Apparently, if we shine light on the electron, what can happen to the electron?
It's fine. Good.
Gone, right? It is emitted, it leaves the atom
Yes.
and is collected on that metal post and creates a current. But the light had to have a particular frequency in order to make it work. And they're like, depending on the metal. So if I used a different metal, it was different.
Could it change?
Yeah, it changed.
Yeah.
So if they used iron or aluminum or tin
It'll
or
change
copper,
the reaction.
it'll change, right? For any metal, that's a set frequency, but a different metal is going to be a different frequency. Why would an electron need more or less energy to be removed from an atom? Why would an electron need more or less energy to be removed from an atom? That's a good question. Questions on waves? Questions on this energy idea and like, the analogy I used yesterday too is kind of like this. If I threw this at a glass window,
It'd break. Depends on the
there would
glass.
be a point that it would break, right?
Yes.
But if I throw it soft enough,
It won't break.
it'll bounce off.
Yes.
But once it has just the right amount of
Energy.
energy, what will it do?
Break.
Break, okay? What if I throw it twice as hard? Will it not break?
It'll break.
It'll break.
Yes.
More?
Well,
Broken's
it-
broken.
if it already broke, then it'll go through the window.
Yeah,
Right.
broken's broken. So this kind of gets to this idea, right? This quantum, like, if I throw it at the glass window soft enough, nothing's gonna happen. And then at some energy, it's gonna break.
Yes. And then you can't.
But if I throw it harder, like so
It's
I
already
reset. I get a new glass window,
It breaks.
and I throw it with a frequency of 6.
It breaks.
Still
Well, it breaks.
Yes.
It's not gonna break more.
No.
It's just gonna be broken
It'll just break.
because it already had the energy needed to break.
Yes.
Yes.
The glass might go farther, but it's not gonna break anymore.
That's right. It's not gonna break it. The electron. So now he relates this to the electrons, right? So the electron's already gone. You can't make it more gone. Right. It absorbed the energy it needed, and now gone. Okay. But I'm gonna leave you with this question because we'll get to this next time. What would cause an electron to need more or less energy? And that's what we'll pick up on Thursday. Okay. Thursday. Yeah, Thursday, maybe. Well, maybe Thursday. We'll see. Okay. Questions?